This is a graphics engine made from scratch using JavaScript and WebGL. You're probably used to graphics engines being rendered primarily with low-level languages, but in this video we're going to try something different by using a not so commonly used language along with a graphics API to utilize the GPU. We're going to start simple, from Hello Triangle with basic shader code and slowly building our way up to 3D objects, transformations, textures, cameras, 3D models, and lighting. We're going to be using math equations and some coding magic to simulate real 3D graphics. We'll start by setting up our canvas with the WebGL context and displaying a blank space. To no surprise, graphics programming has many parts to it, but the foundation of it all is a little something called shaders. Shaders in simple terms are just programs that run on the GPU. They are written in a language called GLSL and are split mainly into two parts, the vertex shader and the fragment shader. Think of it like a brush and a color palette. The vertex shader tells the GPU where to draw something, the fragment shader tells the GPU what color to draw. A bit of an oversimplification, but that's basically the gist. Together they make something called a shader program. The vertex shader runs once for every vertex in your world, while the fragment shader runs for every pixel inside the shapes those vertices form, like a triangle. We use them by passing data of our vertices and colors from our JavaScript to the vertex shader. The vertex shader then shares the data to the fragment shader, which does the coloring calculations. At the start, you probably only need one shader program to get things working. Later on, as you add more effects like lighting and textures, you can create additional shaders for different purposes. For my engine, we only write two shader programs, one for ranging our objects and the other for light sources. Sounds confusing? Don't worry. Let's start with writing a simple shader code to draw a triangle. For syntax highlighting, we will write our shaders as inline scripts in the HTML. The vertex shader will take in a position vector and a color vector, along with an out variable to pass the final color to the fragment shader. We set up our main function. We assign the final position of our vertex in clip space using the built-in variable gPosition. It takes only vec4 values, so we wrap our vec3 position in vec4 and pass in 1 as the fourth value. This is used later by the GPU for perspective division, so it knows where on our canvas the vertex ends up. Lastly, we assign the given color to the final color. We make another script for our fragment shader. You need to declare a floating point precision, otherwise we get an error. Medium is usually the standard. We take in our color from the vertex shader and we just set our final color to the given color. In our JavaScript, we create an array of vertices for our triangle in clip space coordinates. We write a function to compile our shaders. We create something called a buffer, which is just a container to store our data for the GPU. Think of it like a lunchbox of numbers. We pack the lunch the GPU eats. We assign our vertices to the buffer, create a buffer for it to store the data. We compile our shaders, create a shader program, link our shaders to the program, add a little check condition in case of errors, then we just use the program. The variables we created in our shaders each have unique attributes called locations. Think of them as gates or puzzles to the underworld, the GPU of course. So we need to get these locations based on the variable names we gave them and send our data. We bind our position location to the vertex buffer. We then tell the GPU how we want them to be read. Index is the location itself for the data. Size is how many in the array it should take per vertex. That's 3, XYZ. The type is float. It's already in float, so we don't need to normalize it. Then the rest are just specifics on how it should be read. We want everything to be read as it is, so we'll set them to 0. We do the exact same thing for colors, and then finally we draw in our render loop. And look at that, our first triangle. Pretty sick. I know, it's a lot of work for one triangle, but once you get this down, everything else is just beauty, not about this. Now, triangles are cool, but I want to make something in 3D. Rendering 3D objects is pretty much the same, only difference is the change of vertices. A cube, for instance, has 6 faces. For each face, we have to create 6 vertices, each with their XYZ coordinates. But a square only has 4 points, not 6. Yes, but sadly the GPU only understands triangles, so a square can be divided into 2 triangles with 3 vertices each, making 6 in total for one face of the cube. We unfortunately have to account for all 6, even if some of the values are repeated. You complete it. Divine, calm down. For colors, we want each face to have a distinct color, so we give all 6 vertices for each face the same color. That's way too long to write down, so I will just create a matrix for each face's color. They just repeat each one 6 times and spread the values in an array. And we have a cube. Well, sort of. It's a bit distorted because we don't have a projection matrix, but we'll get to that in a bit. Also, we can't see the other side yet because we need some sort of rotation happening. Shit. This is where matrix multiplication comes in. In computer graphics, there are 3 major matrices you work with. The first one is the model matrix. Think of it like a makeup artist. You just stand there and they apply all sorts of transformations to you, things like rotation, scaling, and positioning. Next is the view matrix. This is like a cameraman. They don't touch you at all, they just move around the stage, step closer, step back, or change their angle. This decides what part of the scene actually shows up in the screen. Finally, the projection matrix. This is like the lens you put on the camera. Wide angle, zoomed in, or even fisheye. It decides how the 3D world gets squashed into the 2D screen. In our vertex shader, we need to create variables for all 3 matrices. Then in our final GL position, we multiply all 3 of them with our vertex position. The order we multiply is also important. We first apply our lenses, then set the camera, apply the makeup, and lastly set our position. In concept, it's actually meant to be in reverse, but because of how matrix math works, we have to write it this way instead. In our JavaScript, I really don't want to go through the pain of doing matrix calculations by hand, so I'll be using a library called GL Matrix. They have some built-in matrix functions and vectors we can use, just to make our code a lot more easy to manage. We can actually wrap our cube code into a function and just store essential data in a cube object. This is also where we apply our model matrix. Outside the function, we create a cube, set up our view matrix and projection matrix, then use these functions to apply our perspective. Our field of view will be 45 degrees in radians. Our aspect ratio will be the canvas width divided by the canvas height, and the rest are our near plane and far plane respectively, meaning anything closer than 0.1 or further than 10 will be clipped. We link everything to our locations in the shaders, create an angle variable. In our render loop, we initiate the cube, we apply our makeup, we apply some X and Y rotations, we finally send all matrices to their respective shader locations, and finally we draw. And look at that, a spinning cube. But the colors look like crap. Let's add textures to it. Textures are mapped on 3D objects by passing their edges as UV coordinates for each vertex of that object. 0, 0 being the bottom left, 1, 1 being the bottom right, and so on. We first need to create locations in our shaders for textures instead of a color, and then all we have to do is create an array of these UV coordinate values in the order of their respective vertices. Initiate our textures using GL functions, send the data to our texture location, and voila. Now let's try and add proper camera movements. The goal is to simulate a human walking in a 3D space. To do this, there are 4 main variables to work with: position, where the person is, direction, where they are facing, and finally their head rotations. We'll call this pitch and yaw. Pitch for vertical, yaw for horizontal. We actually don't give yaw 0 at first because by default it looks towards the right of the x-axis because it's horizontal. What we actually want is for it to look towards the z coordinate, meaning rotating it backwards minus 90 degrees. So instead set its initial value to minus pi divided by 2, meaning minus 90 degrees. Next, we listen for some keyboard inputs. Then we create a function that makes changes to the variables based on the key presses. Our pitch and yaw determines what direction the camera is facing, so we need to convert their values to direction vectors using simple trigonometric formulas. Then we actually have to create a separate direction with no pitch. This direction is actually what we'll use for movements. If we don't do this, the camera begins to fly upwards when we look up, which isn't how, well, walking works. We also need a strafe direction variable for moving left and right. This is so we can keep track of where our left and right directions are, regardless of where we're facing. The rest is straightforward. We just scale our directions and add to our positions based on this variable and our movement velocity. Then we add 4 more controls for adjusting our yaw and pitch. Then in our loop, we create a target, which is just a point in front of the camera. Lastly, we just build our view matrix around everything. The outputs are eye position, where the eye is looking at, and what direction is up, which is the y-axis. And we have a walking camera. Pretty sick. Now we have to do some code refactoring, because having everything in just one file is getting way too chaotic. Don't worry about this though, we're just making more script files and separating parts of the code based on concerns. And look at that, we have a much more refined code base. Now, similar to modern 3D libraries, we have a cube class. It has 3 functions, one for initializing the shaders, another for initializing buffers, and a draw function. I then went on to make a similar class called planes, which is just a rectangle for rendering things like floors and ceilings. It's just one face of a cube, so its code is straightforward. We also have a scene class to house and render all objects of our world, a file to store all global variables, a file for controls, a utility file for functions like compiling shaders and loading textures, and lastly, our main file. This is where we construct our world objects and run our engine loop. Now we can render as many objects as we want. Now when I said I made this from scratch, I literally meant from scratch. This entire structure is written by hand. No Blender, no nothing. And not because I didn't want to, I just don't know how to use these softwares. I have literally never touched Blender before in my life. So it took me like 2 days, but I made something that looked somewhat decent for the video. After I was done, I noticed the camera felt a little stiff, like we're sliding on ice instead of walking. Modern FPS games have this sway left and right movements when you move around. They do this to make the movement feel more realistic, like you're actually walking. And it's actually quite simple how this is done. We just need a function that adds a bob and sway movement to our camera. We use delta time to control the speed. Of course, we only want it to happen when we move. Then we just use the sine and cosine of the variables to create wave-like movements, up, down, left, and right. We then clone our camera position, add the effects, and return the new position. Then in our game loop, we just call the effects and replace target with the new position. Now our movements feel a lot more realistic. It gets boring just staring at cubes and planes all day, so let's add a 3D model. I found this cool model of Jesus, my Lord and Savior, on this website CG Trader. They provide a bunch of really nice models for free, so definitely check them out. Now, big question, how the heck do you load 3D models? Well, 3D models come in different file types, OBJ being the most common and one we'll be using. It's very simple to understand. I mean, you can literally open it on Notepad, and it has everything you need: vertices, UVs, normals, etc. except animations. You might want to use a different extraction for that. So all we need is a model class similar to our cube and planes. But this time we read the vertices and UVs from the OBJ file rather than hard coding it ourselves. The OBJ data is arranged in a recognizable pattern, so we just use that to extract the numbers. I'm not sure what the size of the model is, so we won't scale it just yet. I wonder where it is.
Later that same evening.
Yeah, that's way too big. Let's reduce the size a bit. Much better. Now for the final piece of the engine, lights. This involves something called the Phong light model, or the Phong. I'm not sure exactly how you pronounce this. It has the ambient light, which is just the room's light color, diffuse light, which is the direct light hitting a surface, and circular light, which is this shiny highlight you're seeing. Every vertex has a normal, which is a vector perpendicular to its surface. It's to tell us whether a surface is facing towards the light source or not. The concept of light itself is simply multiplying colors. If a red light hits a blue surface, nothing shows, because both colors cancel out. If a red light hits a red surface, we just get red. And that's basically the gist. First of all, our light sources won't be affected by lights themselves, because, well, they are the bloody lights. So we need a separate set of shaders for light sources, one that won't have any ambience, diffuse, or circular variables. Not even a texture, just the coolest one. In JavaScript, we create a separate class called lights, which is essentially just another cube, but we use these new shaders instead. We also need a variable for our light source, its color and initial position. Then we can create materials that react differently to our light source, like gold and plastic. Next, we need the normals of all vertices. Models already have them in their OBJ file, so we just extract them like the rest. But for our cubes and planes, we need to write them by hand. It's very simple. The front face is z plus 1, the back face is z minus 1, left is x minus 1, right x plus 1, top y minus 1, and bottom y plus 1. For planes, it's just the front face, so z plus 1. Then we just need to send all our light specifics along with the normal vector to the shaders. The shader is where we do our light calculations. We first need to send the world position of our vector, which is where the hell it actually is in our world, and also its normal vector. And we calculate them like this. In our fragment shader, we get these two variables as well as the light specifics of that object. Next, we need the light direction, which is where the light is coming from, and the view direction, which is where the camera is facing from. We convert our normal vector to a unit vector to make sure it's always 1. Then we just need to apply the classic Phong lighting formulas for the ambient, diffuse, and specular light. The resulting color being the combination of all three. And voila, we have lighting. I was curious to see what it would be like to have more than one light source, but I won't explain it just yet. I'll leave it as a fun challenge for you guys to try out. The comment with the best answer will be pinned. Sadly, this is where it all ends. As usual, I've made the source code available on my GitHub, link in the description. Hopefully you found this video useful or at the very least entertaining. As always, thank you so much for watching, and more importantly, always remember, God loves you. Catch you in the next one.